and welcome back to Cap That Flag. Today we're continuing our picoCTF series with a challenge called Stonks. It's worth 20 points, it's from picoCTF 2021, and it's in the binary exploitation category. The description reads, I decided to try something no one else has before. I made a bot to automatically trade stonks for me using AI and machine learning. I wouldn't believe you if you told me it's unsecure. So we've got a link to some C source code, as well as a netcat command to connect to a picoCTF server. So as always, we'll pull down the available file and then we'll get started. Let's start by using that netcat command to connect to the picoCTF server and see what we get. It says, welcome back to the trading app, and we have options to buy some stonks or view my portfolio, and it's waiting for input. So let's start by buying some stonks using patented AI algorithms to buy stonks. Stonks chosen. What is your API token? So it's asking for an API token. If I just give it 123, buying stonks with token 123, and we have some stonks, and it then says goodbye. Okay, so clear out of that with Control C. So if I run it again, and then I go option 2, view my portfolio, you don't own any stonks. Goodbye. Okay. So now let's have a look at the source code. So presumably this source code would compile into the application that we just connected to on the picoCTF server. So this is going to make it easier for us to find a vulnerability in the code by letting us view the actual source code and not having to attack it as if it's a black box. So we've got a flag buffer up here, which could be relevant. Anything with flag in it we want to pay attention to. It's got a couple of struct objects for stonks or portfolios. I'm going to hide some of the stuff I don't think is relevant. Got a view portfolio. So the view portfolio method doesn't give us any way to interact with the program while we're in there. So I don't think that's relevant either. Again, I don't think this bit's relevant. Okay. So in this buy stonks method, we have this flag buffer again. So flag buffer set to 128. So we're making a character array of size 128. And then we're opening a file. Then we're going to move the contents of that file into our character array. So this API underscore buff variable will most likely hold the flag contents. So let's have a look what else this method does. So I think this is all pretty irrelevant. So this is the area where I feel like we'd be able to exploit the program and the vulnerability would be. So we're allocating some space to this user underscore buff variable. And then we read in the user input using scanf and are storing it in user underscore buff. Because we have this input here, which is then printed back out here, we may have the option of using a format string attack. So we should be able to craft the input here, including specific characters that are format string parameters, which will then allow us to dump some of the contents of the stack back to us, which should include this API underscore buff variable that we are hoping contains the flag. So I want to explain how this attack works, and to start with, look at how printf is normally used and how placeholders in strings are normally used. So this code here, you see the value of test1 is, and then it has a %sign D. So this is a placeholder within the string, and the next argument for printf, in this case test1, will be substituted into this position when printf is run. So because test1 variable is equal to 123, and we're assigning this test1 variable to this part of the string, then we would expect the output to be the value of test1 is 123. So let's just check that is the case. So there we go. That's what we expected. This also supports multiple placeholders. So if we wanted to change this to add another variable, so this should also work. We're going to have to compile this, but just do that now. So you could have multiple placeholders in the string. 1, 2, for 1, 2. Now the interesting thing is, if we copy this here, and we don't supply these arguments, this will still technically work. And we will get some warnings when we compile this. But it's quite interesting to see what happens when this actually runs. So I'm going to save that again and recompile. We've got some warnings about this exact thing. And then if we run, that second line is still working the exact same way, even though we didn't specify arguments. Because there's no other arguments given to the function, this first %d will grab the top of the stack to supply the value for this placeholder. The second placeholder will grab the second element of the stack. So the reason this works is because this printf function runs first, and it leaves test1 and test2 on top of the stack. So when this printf function runs, and it grabs the top of the stack for this %d and the second on the stack for this %d, it's still grabbing test1 and test2. But the main takeaway is, if we don't supply the variables to the printf function for these string placeholders, the function will just pull values off the stack instead. So there's a lot more to these placeholders within strings for printf, and I'm not going to go through everything, but one thing I will cover off is that the character used after the % determines what type of data it wants to pull in. So I use %d in the example before, which is for it will give you an integer. We can use an x to give us a hexadecimal number. S can be a string. We'll probably use the x when we're solving the challenge. So now we've dug into printf a little bit more, and we understand these placeholder elements. We understand we don't need to add the additional arguments to the function for it to work. And if we don't, we can then pull elements off the stack. Here's some test code that just shows that process in action. So I've just created 3 local variables. And when this code's compiled and run, those variables will exist in memory on the stack. And then the printf command underneath is just going to grab the top 10 elements from the stack. And we'll hopefully see our other variables listed when we run it. So here's the output from the command, and these values represent the 3 local variables we created in our code. We jump back here, 7b, 1c8, 315. So we've demonstrated that we can pull the value of variables off the stack using this technique. So getting back to the challenge, now we're going to compile the source code that we have into an executable, and we're going to start playing around with that executable to see if we can achieve a similar result using the same technique. So we'll compile, and this warning that's appearing is actually related to this vulnerability we're trying to exploit right now. So let's just confirm we can run the compile program. And it looks like it works. Except we're missing one component, and that's the actual file that the code reads that contains the flag. So if we go back to the source code, the code tries to open a file named API. Because it doesn't work, we're getting this error being printed out. So we'll create this API file and we'll go from there. So for now, I'm just going to make the flag A, B, C, D. Okay, and then I'm going to run the Stonks program again. So that looks like that's working. I'm going to try inputting a whole bunch of percentage X's. So we're back on our ASCII table again, and the flag I set was A, B, C, D in capitals. So we're looking for 41, 42, 43, and 44. And if you look at the very last one that we got off the stack, got 41, 42, 43, and 44. So the fact this sequence is here, but in reverse order, just tells us that the data is being stored in a little endian notation. And if you want to know more, you can just look up endianness, or big endian and little endian. So little endian is when the most significant byte is at the smallest memory address, and the least significant byte is at the biggest memory address. So it's kind of in reverse order to what you'd expect it to be. So later on, when we're decoding the real flag, we're going to have to reverse the order of things to get it to read properly. So let's connect to the program running on the picoCTF server now, and we'll use the same technique to dump the stack, and then we might write some code to pull the flag out of the stack data. So I know that the flag is going to start with the word pico. So I'm just going to work out what pico looks like in hex little endian notation. So it's going to be 6F, 63, 69, 70. So this particular hexadecimal number will signify the start of the flag. And reading along, it looks like it is here. Yeah, yes. So we have a match. So we're pretty sure we've now got at least the start of the flag in the stack dump. So the ending of the flag should be where there's a null byte, which is a 00. So I'm just going to highlight everything from here at the start through until I see 00, which is here. So I'll grab that entire byte. So now I should be able to write some Python code that will turn this data into the plain text flag. So I'll go do that now, and then I'll come back and show you what I've written. So here we have the completed code. You can see there's an input string here, is what we pulled out of the stack. And we're going to build up an output string to print at the end. So then we're going to split the input string up into a list. We're going to convert the item into a byte array. Then we're going to reverse the byte array, which fixes the issue we had with the little endian notation. So then I'm looping through every byte in the byte array, and if there's anything that falls outside the normal range for ASCII, I'm going to zero out that byte. And this will take care of these characters here that are off the end of the flag, but they're still included in the data we dumped. And then we build up that output string by converting each byte into the relevant character, and finish by printing the output string. And if we run this now, we get the flag in plain text. So this has been one of my longer videos, and if you're still with me, thank you for making it this far. I'd welcome any feedback you have. If you'd like any more detail about anything in the video, be sure to leave a comment. As always, thanks for watching, and I'll see you in the next one.